Hi, I am Lopamudra Sen. Welcome back to my channel Electronic Science Tutorial. I will start a new lecture series on VLSI technology. Today is the 15th class of this lecture series. Those who are not follow my channel, please follow my channel. If you like my channel, then please like, share and subscribe my channel. सब्सक्राइब की बेल आइकन को प्रेस करके रखिए ताकि जब भी मैं कोई नई वीडियो लेकर आऊँ आपको पता चले. So let's get started. Welcome to VLSI technology series. In previous class of this lecture series, we talk about the various properties of the crystal plane, and we discuss about that only three types of plane we choose in VLSI technology, that is 100 plane, 110 plane and 111 plane, and also discuss about their properties. In today's class, we talk about some of the other properties of these three planes, and from there I will try to correlate how the material properties are governed by these atomic configurations in the planes. Okay? Next slide पे चलते हैं. In this slide, we talk about some of the basic properties of crystal planes, and also we draw some important observation of geometric consideration of planar structure. First observation, that is, we consider two planes x1 y1 z1 and x2 y2 z2. When these two planes are meet, they form an angle between them. If I call this angle is theta, and this plane can be 100 plane, or it can be 110 plane, or it can be 111 plane. Okay. So between these two planes x1 y1 z1 and x2 y2 z2 is given by this relationship, that is cos theta equal to x1 dot x2 plus y1 dot y2 plus z1 dot z2 divided by root over x1 square plus y1 square plus z1 square dot x2 square plus y2 square plus z2 square. Right? Second observation, that is, these planes will intersect at a line. The line direction is given by x, y, z, which I actually means the Miller indices of the planes, where x equal to y1 z2 minus z2 y1, y equal to z1 x2 minus z2 x1, and z equal to x1 y2 minus y1 x2. So this is a, just a minute. So this is a line of intersection between two planes. Okay. And finally the separation between two adjacent parallel planes. Okay. So this front plane or the back plane, which I can't see in this picture, or you can see the top of the plane or the bottom of the plane, which I can't see in this picture. So this is the adjacent parallel plane of this cube, right? So what is the separation between the two adjacent parallel planes? That is D equal to A divided by root over h square plus k square plus l square, where h, k, l are the Miller indices of this plane. So these two relation, one is angle between these two plane, that is cos theta equal to this one, and the second one is the separation between the two adjacent parallel planes. So these two observations are become quite important observation along with the atomic density of each plane, which determine the properties of each particular plane. And this will define you that which crystal orientation is applicable for any particular application. Okay. In this slide, we explore some of the examples and calculate the separation between two planes by using the previous relationship, that is D equal to A divided by root over h square plus k square plus L square. First example, I consider here two 100 plane. Okay, that means I have front plane. I have considered here front plane and the back plane of a cube. Okay, then what is the separation between them? That is D equal to A divided by root over h square plus k square plus L square, that is equal to A divided by root over 1 square plus 0 square plus 0 square, which is equal to A, where h equal to 1, k equal to 0 and L equal to 0. Right? In similar manner, we can again consider two 110 planes. Okay. So, what is the separation between the two 110 planes? That is D equal to A divided by root over 1 square plus 1 square plus 0 square, that is equal to A divided by root 2, where h equal to 1, k equal to 1 and L equal to 0. Right? Next, for 111 plane, that means when we consider two 111 planes, the separation between these two planes, that is D equal to A divided by root over 1 square plus 1 square plus 1 square, that is equal to A divided by root 3, where h equal to 1, k equal to 1 and L equal to 1. Right? So, from these three examples, what we see? We see that 111 plane is the least spacing between two adjacent parallel planes, or we can say 111 planes are most closely spaced together. Right? So, this is very important observation. When we fabricate any device, what we need? First of all, we need a block of single crystal silicon. Right? Single crystal silicon is generally grown from the melt, and when you are solidifying the melt under controlled condition, it is easiest to grow it in the 111 direction, because the 111 planes are most closely spaced together. Okay, that means it is easier for the crystal to grow in that direction with the least spacing between adjacent plane. So it can just grow very easily in that particular direction. So it is very easy to grow. So it is much simpler to grow 111 crystal than if you want to grow the crystal in 100 or 110 direction. Okay. So that's why we use 111 crystal orientation in VLSI technology. Right. So here we end today's session. Thank you. If you like my video, then please like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.